Greetings, ladies and gents, and welcome back. It's Mike Medicine Science Club. In this video, we'll be looking at a question which was written in November 2020. It's a question on electric circuits. So in this case, they say that a battery with an internal resistance of 0.5 ohm and a known EMF is connected to three resistors, a high resistance voltmeter and an ammeter of negligible resistance, as shown in the circuit diagram below. They say that the resistance of the connecting wires must be ignored, meaning that of course these wires, of course, that were used in this case do not take or consume any of the energy, of course, that would actually be provided by the battery. So that's what that, of course, that's that statement mean. So in this case, for 8.1, they said that define the term EMF of a battery. So in this case, to define that, now I'm not gonna write that down, I'm just simply gonna say it. So in this case, EMF, that's the maximum energy provided by a battery per coulomb or per unit charge passing through it. So that would actually be the formal definition that you would need to give, of course, when you are writing the exams. So in this case, that would be for 8.1. So for 8.2, of course, the statement before this is that the rating on the voltmeter decreases by 1.5 volts when switch S is closed. Now remember that, of course, whenever, now remember that of course a battery, right, is designed to provide us with a certain amount of energy, right? But in this case, due to internal collisions that happens inside the battery, so in this case the energy that you actually get at the end, or the one that would actually be distributed to your circuits, would actually be less than the one that is designed of course for the battery to give us. The reason for that would be, of course, there is, of course, some of the energy was lost due to internal collisions inside the battery. So in this case, now suppose, let's say you had a battery, all right, and then of course they say that of course this battery is designed to give you 20 volts, all right. So in this case, now immediately, let's say immediately after you connect that that battery to a circuit that is a switch, that has a switch that is closed. Now suppose, let's say it drops by 0 point, let's say it drops to 18 volts. So in this case, that drop in value, in this case, that would actually represent the energy that is actually lost inside the battery due to internal collisions that happens there, in this case, which they designed as the internal resistance. So in this case, that drop, or that 2 volts, of course, referring to the example, that 2 volts would actually be the volt, in this case, that is actually used by the internal resistance. So in this case, they say that the reading on the voltmeter decreases by 1.5 volts when switches is closed. So in this case, we know that of course that 1.5 would be the voltage that is actually used inside the battery by that internal resistance, that small r there. So in this case, they said that give a reason why the voltmeter reading decreases. So that's for 8.2. So in this case, the reason for that would be because of course the voltmeter decreased because, of course, the energy is actually converted in the battery due to internal resistance. So we said that of course due to the internal collisions that happens inside the battery. So in this case, we would actually lose some of the energy, right, inside the battery before the energy even gets to our external circuit. So that would be for 8.2. So for 8.3.1, they say that calculate the following when switch S is closed. So in this case, for 8.3.1, they want the reading on the ammeter. Now remember that of course, now if of course coming out of our battery, right, would be of course the total current, right? So in this case, this would be a total current traveling there, of course, when switch S is closed. All right, so in this case there will be total current. But as soon as it gets to that node, we know that of course some of the current would go to that side, and then of course some of the current would go that direction. So in this case, this is where our current is split, right? So in this case, of course, but when it gets, of course, to that node again, so in this case our current in this case becomes 1 again. So in this case, we know that of course there we would have the total current. So in this case, so to calculate the current that is actually passing through that ammeter, what I'm going to do, so I know that of course the current that is passing through that internal resistance would actually be the same current that passes through that point. So what I'm gonna do, I'm just gonna use that the information. Now remember that of course I have more information on that internal resistance, and on that internal resistance I know V, right, the voltage that is actually used by that internal resistance, and I know that I know the resistance of that resistor to be 0.5. So what I'm gonna do, I'm gonna use Ohm's law, which says, so in this case this will be answering for 8.3.1. so in this case for 8.3.1. so in this case what we know is that of course R, or I, is actually equals to V divided by R. So in this case I'm just gonna represent it by small letter R. So in this case let me just say R. Let me just put it in capital letter so that it doesn't confuse. So in this case this will be RR. And this is V. This voltage would be the voltage that is actually used by that internal resistance VR. So in this case this would actually be the current that is passing through that internal resistance again, which is R. So I know that of course I'm looking for the current, right? So in this case I know that I would be equals to, I know that the voltage passing through that resistance would be 1.5. Right, so that would be 1.5 divided by the resistance of that resistor, which is 0.5. So if I put that into the calculator, so this would be, so that's 1.5 divided by what was that value, 0.5. So we know that of course the current would be 3. So this would be 3 amperes. So that would be the units for current. So this would be the current that is passing through that internal resistance. So as a result, we know that of course this would be the total current. So in this case we know that of course the current passing through that point A, that ammeter A, in this case would be the total current. So in this case we would conclude therefore the current that is passing through ammeter A would be equals to 3 amperes. So that would be answering for question 3, for question 8.3.1. So in this case for 8.3.2, they say that calculate the total external resistance of the circuit. So of course to calculate the total external resistance of the circuit, so what we do is that now if you look at that diagram, we have these two resistance that we have here being parallel to one another, right? R2 and R3 are parallel to one another. So what I'm gonna do in this case, I'm just gonna calculate R parallel first and find the value for that, and then in this case I would simply just add it to that 4 resistor there. So in this case we know, of course, now remember that of course when you calculate R parallel, we are simply just combining this, making it as 1. So in this case, after they've become 1, what would actually have in this case would actually have that being in series with that R1. So in this case what I'm going to do would be to say R parallel. So this is, we know, let me just scroll down. So we know that of course R parallel, so R parallel is actually equals to so that would be 1 over R1 plus 1 over R2 plus 1 over R3, and of course until there plus that, but in this case you just simply put it to the power -1. So in this case that would be, of course there's that original version which says of course 1 over R parallel is equals to 1 over R1 plus 1 over R2 plus, and of course until to the last one. So this is actually the same thing. What I did was that of course, now remember that of course at the end we would need of course to invert that answer that we get, right? So in this case I just simply did that, before we even get there. So in this case this would simply be equals to 1 over R1. Now in this case this would be R2, right? So in this case this would be 1 over 25 plus 1 over 15, right? So in this case we put that to the power -1. So if we put that into the calculator, we say that would be 1, let me just close brackets, so that's 1 over 25 plus, that's 1 over 25, just so that would be 25 plus 1 over 15. In this case we put that to the power -1, so that would be -1 there. So in this case what you would get would be R parallel being 9 point, so in this case this would simply be 75 over 8, which is actually equivalent to 9.375375 ohms. So we know that of course this would be R parallel. So in this case, to calculate the total external resistance, so what we would do in this case would be, let me just scroll down again. So what we have would be, so I know that of course now R total would simply equals to R series plus in this case that R parallels. In this case, I know that that R series would be, I think that was 4 ohms plus that 9.375 ohms. Now you can't round that off early. You are not allowed to round off unless that's the final answer, right? So in this case, if you put that into the calculator, so what I'm simply going to do would be to say plus, so that would be plus 4. Right, let me just scroll up, just to make sure that, so that was actually 4. So in this case, if I take that back, so in this case what we have would be 13. So that would be 13. So this would be, let me just put back to the pen again. So this would be 13 point, so this would be 13.738. So this would be 13.38. Now we can round off since it's the final answer. So in this case, this would be ohms. So that would be the solution for 8.3.2. So in this case, for 8.3.3, they said that calculate the EMF of the battery. So we know that of course to calculate the EMF, we have the equation, right, that we have. Let me just split this so that we have somewhere to write rather. Let me just start from here. I'm not gonna erase that, so in case if we need these values. So in this case, what we know of course to calculate the EMF, we know that of course EMF would be, so we know that of course EMF, right, which is equals to I multiplied by R plus small letter r. So in this case, that R, that capital letter R would represent the total external resistance, and of course that small r would represent the internal resistance. But what you need to take a note of would be that I there. So that I there would be the total current that is actually passing through our circuits. So in this case, we know that of course we know the total current. We said that was 3, right? So we multiply that by R, which is 13.38. This would be 13.38 plus 0.5. So in this case, if you put that into the calculator now, again, you can use the rounded version now. Why? Because we are actually looking at another question. So this would be, so let me just, so this was 3 multiplied by, so that was actually 13.38 plus 0.5. So this is 0.5. So this is what we have would be 41.64. So that would be the EMF of the battery. So that would be 41.64. So that's would be, so in this case we know that that was 41.64 volts. So in this case, that would be the value of the EMF. So in this case, for the last question, so there's another question down there, which is 8.4. So they said that Elena makes the following statement. They said that the current passing through R3 is larger than the current passing through R2. So what this student is simply saying that the current that is passing through R3 is actually greater than the one that is actually passing through R2. So in this case, they say that is this statement correct? Choose from yes or no. Explain the answer. So the answer of that to that would simply be yes. Why? Because in this case, now the first thing that you must note is that in this case, the current, the voltage that is passing through this resistors that we have in this case would be the same, right? But in this case, so what you need to note is that whenever you have resistors that are parallel to one another, the one that actually have the high resistance, so the current that will be passing through that would actually be less than the one that is passing through the one that is a lower resistance. So the resistance that or the resistor that has a high resistance, in this case the current that would be passing through that would be less, and the resistor that is a low resistance would actually have a high current passing through it. So in this case, of course, to answer that, they said that, of course, is this statement correct? So we said yes. The reason for that would be, of course, the higher the resistance, in this case, the lower the current passing through it. So that would be, of course, for 8.4. So they say that 8.5, the 4 ohm resistor is now removed from the circuit. How would this affect the EMF of the battery? Choose from increases, decreases, or remains the same. I'm sure you already know the answer to that. We know that, of course, the EMF will actually remain the same. Why? Because now remember that whatever is happening through to our, in our circuits doesn't actually influence the amount that is actually provided by the battery. So in this case, the answer to that would be remain the same. So this would be the end of today's lessons, ladies and gentlemen. And of course, if this helped at some point, be sure to like the video. And of course, if you haven't subscribed, be sure to hit that subscribe button. And of course, don't forget to hit that notification bell so that when the next video comes up, you'll be the first to be notified. Now, if you have got any questions, you are more than welcome to throw that in the comment section. And of course, if you have again any question, like any question paper that you would like me to cover, of course, you are more than welcome to just throw that in the comment section. Or make sure that I cover it. But as the story always ends, ladies and gentlemen, this is Mike signing out. Sharp sharp.